Hey guys, it's Miss Johnson and I'm here to bring you our notes video for Unit 7 Note 6, which is on mutually exclusive and inclusive events. Now, before we get into today's notes, I want you to do me a favor and flip back to yesterday's notes. Go back to Unit 7 Notes 5, which is on independent and dependent events. Up at the top, somewhere in that white space kind of by your name, I want you to tell yourself that these were and probabilities. And probabilities. So this is on our independent and dependent events. Okay, these were what we call and probabilities or both probabilities or all. All those words tell you that you're looking at independent and dependent events, and they all mean multiply your probabilities. Okay. You're multiplying your probabilities in this one. So that's on your independent events one. Now, the reason I make a big point about that is because with our mutually exclusive and inclusive events, these are what we're lovingly going to call or probabilities. Okay, so you could write that up at the top of this notes page, or probabilities. Okay, and when we have or probabilities, we're going to be adding and subtracting today. That's how that's going to be a little different than yesterday. So let's just look at our example up at the top. It says a bag contains 8 red marbles, 12 blue marbles, 9 yellow marbles, and 11 green. A marble is drawn at random. Find the probability that the marble drawn is either blue or green. So we're looking for an either blue or green marble. So that means our successes are the blue, which is 12, and the green, which is 11. 12 plus 11. So I have 12 plus 11 successes, which is 23. I also need to know the total. Total number of marbles is 40. So that would be my probability, which is equal to 0.575. Okay, so notice that I had to look at two different successes there. I needed to look at the number of blue and the number of green, and I needed to combine them together. So that's what mutually exclusive events are. So when we get into mutually exclusive events, we're looking at events that don't affect each other. So for example, rolling a 5 and flipping a tails. That's the probability of A or B, means I take those two probabilities and add them together. And then inclusive events, events that do affect each other, they're events that make a difference on one another. For example, rolling a number less than 3 or a 1. Well, 1 is also less than 3, so you counted it in both places. You can't count it in both places. So we're going to have a probability plus another probability of less than 3, probability of 1, and subtract the overlap. Okay, so we're going to look at these two probabilities today. But again, these are adding and subtracting probabilities. Notice that we're not multiplying anymore. So let's just talk about identifying these. In number 1, it says drawing a heart or a diamond from a standard deck of cards. Heart or a diamond. So now this is where you have to ask yourself, you're looking at an or probability. Is there anything in the hearts that's also in the diamonds? Well, no, it's not possible to be a heart or and a diamond at the same time. So there's no crossover between the two things that I'm looking at, which means these are mutually exclusive events. They're exclusive of each other. Okay. Now, if I look at number 2, drawing an ace or a spade, well, there is one card that is an ace of spades. So that means these are inclusive because there's crossover. There's something that fits into both categories. If I look at number 3, it says rolling a 5 or a number greater than 3. 5, so this is one of my events, or a number greater than 3, that's the other one. Well, numbers greater than 3 are 3, 4, or not 3, I guess, greater than 3 would be 4, 5, and 6. Well, hello, that's in both parts. I can't do that, that's not okay. So I have to call these inclusive events. These are events that have crossover, okay? So then number 4, picking a red or a blue M&M out of a bag of M&Ms. Now we're going to assume that all M&Ms are solid colored. They're not multicolored. So red or blue would be mutually exclusive because there's not an M&M that's red and blue at the same time. Okay, so now let's actually practice calculating some of these things on the back. So if I look at number 5, it says one teacher must be chosen to supervise a class fundraiser. There are 12 math teachers, 9 language arts, 8 social studies, and 10 science. If a teacher is chosen at random, what is the probability that a teacher is either a language arts or a social studies? Okay, either language arts or social studies. So you have two things that you're looking at here, and you have to decide your successes for language arts, your successes for social studies, and is there anything in the both category? Okay, well, typically speaking, if a teacher teaches in the English world, they don't necessarily teach in the social studies world. Now, we know that that's not always the case, but typically speaking, we're thinking that there's no crossover between these two groups of teachers. So that means I don't need to worry about what's in the both, and I know I'm looking at mutually exclusive events. Now I know that these are or, so I'm going to put a little plus sign by the or because that tells me that I need to add. So I'm also adding these. You can tell yourself that there. So then let's look at these actual probabilities. So the probability of being a language arts teacher, we first need to know the total. I have 12 plus 9 plus 8 plus 10. So there are 39 total teachers. And then the language arts teachers, there are 9 of them. So 9 out of 39. And then social studies, I have 8 out of 39. Notice that my denominator didn't change because you're only picking out one teacher. What is the probability that okay, you're only picking out one teacher, so we're not worried about picking something here and picking something there. We just want to know what are the successes if we put these two things together. So our denominator does not change in these. So then if I add these two together, I have 9 plus 8, which is 17. And when we add fractions, I see this mistake all the time. When you add fractions, the denominator stays the same. If you need to write that down, write it down. Denominator stays the same when adding fractions. Common mistake that I see a lot. People want to add those denominators together. Well, think of it like pieces of a pie. You have 9 pieces out of 39 pieces of a pie, 8 pieces out of 39 pieces of a pie. When you put those 9 and 8 pieces together, there aren't all of a sudden 78 pieces of a pie. That doesn't make any sense. Okay, there's still only 39 pieces. You're just taking the 9 and the 8 and putting them together. Okay, so if you kind of think about it that way. But write that note down. The denominator stays the same when you're adding fractions. When we multiplied fractions, we multiplied the denominators as well. But in adding fractions, we keep them the same. Okay, so number 6, it says suppose that out of 1,400 students, 550 take Spanish, 700 take biology, and 400 take both. What is the probability that a student selected at random takes Spanish or biology? So those are my successes: Spanish, biology, and then I need to ask myself, is there any in the both category? Well, it even says the word both. 400 take both. So I know that these are inclusive events, and I know that I'm going to need to subtract those both away. So I'm taking the Spanish, and I'm adding the biology, and I'm subtracting the both. And we'll talk about why we do that. So I know the total number of students are 1,400. I know that 550 take Spanish. So my successes for Spanish are 550 out of 1,400. Then I need to add the biology. 700 out of 1,400. So success for Spanish, success for biology. Now, here's the problem. Let's say I pick you out as a student, and you're a student who takes both Spanish and biology. Now, you have been counted in this category in these successes. Okay, you've been counted there. And you've also been counted there because you're in the Spanish group and you're also in the biology group. So that's a problem. You are only one person and I cannot count you twice. I can only count you one time. So what happens is I need to subtract the both. So I'm going to subtract 400 out of 1,400. Okay, so that's why I have to take those away because I can't count you 2 different times. If you're in both categories, that doesn't work. So when I put these together, 550 plus 700 minus 400 is equal to 850 out of 1400, which is approximately 0.607. Okay, so there's my probability there. Let's take a look at number 7. There are 2,400 subscribers on to an internet service provider. Of these, 1,200 own HP computers, 500 own Dell, and 100 own both. What is the probability that a subscriber selected at random owns either an HP or a Dell? And I shouldn't have, or I should have signified that. This or tells me that I'm adding. Or means add. So I'm looking for HP plus Dell, and I need to ask myself if there's any in the both category. Okay, so my successes for HP are 1,200 out of the total 2,400. My successes for Dell are 500 out of the same 2,400. But again, 100 of those people own both. And since we know that there's some crossover between the two categories, there's some people that are in here and in here, I need to subtract those 100 away. That also tells me that these are inclusive events because there is crossover. If there's anything in this both category, that automatically tells you that they're inclusive. So when I put these together, 1,200 plus 500 minus 100 gives me 1,600. And notice that my denominator stays the same. I don't add my denominators. Do not combine your denominators. This is like pieces of a pizza. The way the pizza is cut does not change. Okay, so this is 1,600 out of 1,400, or 1,600 out of 2,400, which is 2/3 or 0.667 if I'm going to round that. Okay. Next one, number 8. In number 8, it says there's 4 algebra books, 3 literature books, 2 biology books on a shelf. If the book is chosen at random, what is the probability that you select a literature or an algebra book? Okay, so lit or algebra. Now, we want to ask ourselves, is there any way that a book can be a literature book and an algebra book at the same time? I haven't seen it, and I've been teaching a long time, so I think that that is something that doesn't occur. Typically, when you're looking at textbooks for courses, they're either lit or algebra. So I'm going to call these mutually exclusive. And if I'm looking at lit plus algebra minus both, I know that this both category is knocked out because I don't have any in the both category. But I will go back to the lit plus algebra. So I need to know the total. 4 plus 3 plus 2 is 9. And 3 of those are literature. So 3 out of 9 is the successes for my literature books. And then for algebra, 4 out of 9. When I add those together, I get 7 out of 9, which when I do that as a decimal, make that a decimal, it's 0.7 repeating, or if we round it to the third place, it'd be 0.778. Okay. Next one, number 9. In number 9, it says in the game of bingo, balls are numbered 1 through 75. These numbers correspond to columns on a bingo card as shown in the table. A number is selected at random. What is the probability that it is a multiple of 4 or in the O column? Multiple of 4 or in the O column. Okay, so multiple of 4 or in the O column. I'm adding those together, and then I need to also figure out, is there any in the both? Okay, so now we have a couple of lists that we need to make here. I'm going to start with the O column because I think that's a little bit easier. When I look at the O column, I start at number 61 and go up to 75. So there are 15 total numbers in the O column. And the reason I say 15 is because, sure, 75 minus 61 is 14, but I also need to include 61. So there's actually 15. So my successes there are 15. Oh, and by the way, my total is 75 because that's how many numbers there are in the bingo, you know, cage that they have all the numbers in. Then I need to list the multiples of 4. So just off to the side somewhere on your paper, go ahead and start making a list. That's what I did. If I start at the beginning, I'd have 1, 2, 3, 4, then 8, then 12, 16, 20, and so on. And I literally just made this list: 28, 32, 36, 40. 48, 52. See, I'm almost there already. 56, 60, 64. I'm just counting by fours until I get up to 75. 64, 68, 72. The next one would be 76, but I don't have a 76 in my bingo chances, in my bingo cards, so I stop there. So now I need to count how many there are. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So that's 18 out of 75, which are multiples of 4. Now, what about this pesky both column? Is there anything that's in both? Well, sure there are, because there's multiples of 4 that are greater than 61, specifically 64, 68, and 72. So there are 3 of them, which means I need to subtract 3 out of the 75 numbers, because 3 of the 75 numbers were counted in both places. This also, by the way, tells me these are, I'm sorry, hello, not mutually exclusive. These are inclusive events. Erase that. I didn't mean that one. Sorry. There we go. Okay, so now let's put these together. 18 plus 15 minus 3 gives me an even 30. 30 out of 75 is going to be equal to 0.4 as a probability. Number 10, last one. It says a card is drawn from a standard deck of cards. What's the probability of drawing an ace or a face card? And then it tells you in parentheses there, face cards are Jack, Queen, and King, in case you don't remember that from our first day of probability a few days ago. So we want ace plus face card minus both if we have any. Ace or face card, that tells me I'm adding. Then I need to ask myself, is there anything in the ace and the face card category? Well, face cards are Jack, Queen, and King. They don't include aces. So no, these are mutually exclusive, which means I don't need this. Okay. Now let's go back. So of the aces, there are 4 aces out of the 52 cards in a deck. The face cards, they're Jack, Queen, and King, but there's 4 of each of those. So that means there's 12 face cards out of the 52 in a deck. 4 plus 12 gives me 16. So 16 out of 52 is approximately 0.308 for my probability. Okay, so mutually exclusive and inclusive events. These are probabilities or questions that are asking you or, this or that. And anytime you see the or word, you're adding probabilities together, and you need to check for any of that crossover that may overlap to take that away. All right, so thanks for listening for today, and I will see you tomorrow.